Okay, so we went through over the past few classes a lot of different strategies for testing series for convergence and divergence. So we're going to go over a quick review of them, and then we're going to do some problems, and you have to figure out which one we're going to use, and then obviously do that problem. So the first two that we had looked at was the P series and the geometric series. Those are really nice because it allows us to find that exact value for it, and there's an exact rule that we can just look at the problem and find. So the P series is ones that are 1 over n to the p power, and as long as p is greater than 1, it's convergent. If it's less than or equal to 1, it's divergent. And remember, p when it's 1, that's that harmonic series. That's that specific name. Number 2 is the geometric series. Geometric series is of the format a times r to the n power. R is your ratio, and a is your first value. But the ratio, that r is the piece that's really important. If r is less than or is between -1 and 1. So basically, if the absolute value of r is less than 1, it converges. If the absolute value of r is greater than or equal to 1, then it diverges. We might have to manipulate some things around for each of these to get them to actually go up into that setup, but those are the two basic ones. Those two are also the main uses of doing the comparison tests as well. So we try to get it to a P series or a geometric series to compare it to, because those are easy to look at and go, yes, this is going to diverge, or yes, this is going to converge from it. And that's what this one is. If we have something that's similar to a P series or geometric series, but not exactly that, we can use those to compare it. The key piece, though, is remember that if you're doing the comparison, if the original series converges, the series that I'm going to compare it to always has to be less than that series. And if the series that I'm comparing it to diverges, then the series that I'm comparing it has to always be greater than that value there. So otherwise, it doesn't give me any good information. Next few, we have the test for divergence. So if you can look at it and see that the limit does not equal 0, limit equals something other than 0 for that series, then we can just do the test for divergence and do it really quickly. So like if you see a problem that's 5 to the nth power, it's like obviously that one's going to diverge. There's no way that limit equals 0. So therefore, we can just do the test for divergence and be done with it. We don't have to do anything else for it. So that's kind of that catch-all to say this looks completely like it's going to diverge. The limit doesn't work. We have that piece there. The alternating series test is really obvious to see. If it has that -1 to the nth power in front of it, we can do the alternating series test. So anytime you see that -1, I'd go to the alternating series test to see if that works first. Remember, the alternating series test has the two pieces that we have to find out. One, the limit has to equal 0, and the other one, it always has to be decreasing. So those are the two things we have to look at for the alternating series test. Then we had the other two tests. We did the ratio test. That was when we covered on last Tuesday. We did the ratio test, and we did the root test. The ratio test does really well when we have anything with factorials or any constants that are raised to the nth power or products of values. The ratio test works pretty well because we can cancel stuff out. And then the root test is anytime you have something raised to the nth power, because we're doing the nth root, it kind of cancels that part out. So that's really helpful. Now remember, the root test and the ratio test, if the limits are less than 1, it converges. If it's greater than 1, it diverges. And if it equals 1, it doesn't exist. We have to try something else. The final one that we would look at is the integral test. So the integral test is the last one we're going to look at. So that one's the one we really don't want to have to use just because it's a pain to use. But we have that there as the catch-all if none of the other tests actually do work. All right. Let's look at some problems. So here's the first one. So look at it, figure out which test you want to use, and then do the test. So looking at this one quickly, which test do we use for this one?
The alternating series test.
Yep. So there's a quick reminder what the alternating series test is for this one. Those are the two criteria that it has to satisfy. All right, so let's look at the first test. The first criteria, does it satisfy that this series is getting smaller as the n increases?
Yes.
Yes, because the bottom's getting bigger and top's always going to be smaller than the bottom. So yes, we can say that it's going down. All right, so the next thing we have to do is test the limit. Does the limit equal 0? So when we're doing the limit, remember, we're only looking at the n squared minus 1. We're not looking at the other part. So I have the limit as n goes to infinity of n squared minus 1 over n squared plus 1. So I'm going to divide everything by n squared. So I get 1 minus 1 over n squared, and then 1 plus 1 over n squared. So those two are going to 0, so this is going to 1. So it fails the other criteria because it does not equal 0. So this does not converge based on the alternating series test. Remember, the alternating series test does not tell me if it diverges, however. But what's the, if we know it's going to fail the alternating series test, what's the next thing we always want to try? To see if it diverges.
divergence test?
Yeah, we always check the divergence test because, in essence, the majority of cases, like I've only, I think, seen 2 situations where this doesn't actually end up working. And don't ask me to give them because I can't actually remember the series. So the divergence test, we look at this one, so it's -1. We look at the whole series now. So I know this piece is going to 1, so that's going to keep bouncing back and forth. So the limit does not exist. Therefore, it diverges by the test for divergence. Test of divergence. Because that test that has to equal 0 for it to be work.
Do you know it doesn't exist just because that -1 keeps hopping?
Yeah, exactly. That's why I said, like, almost every situation that's going to come up, if it fails the test for convergence, I mean the alternating series test, it's going to it's going to fail the test for divergence, so therefore it diverges.
Okay.
So, and this was the quick. Let me just paste this one in there so you can see that too. And this was the test for divergence. So this limit does not exist, so therefore it is divergent. All right. Next one. All right, which test do we want to try for this one?
Integral test?
Yeah, this one you're going to actually have to do the integral test. There's no easy way to compare it. It's not a p-series or anything else like that, and it doesn't fit any of the other criteria for the other tests. So we kind of have to do the integral test. So this is a reminder of what the integral test was. Just remember, before we do the integral test, it has to meet certain criteria. It has to be continuous, which this one is because it starts at ln of 2, not ln of 1, or n is 2, not n is 1. That's a very important piece because ln of 1 would give me 1/0. It is always positive, and it is decreasing. So it does meet the criteria to do the integral test. So we're looking at the integral from 2 to infinity for this one. So how are we going to do the integral for this one?
U substitution.
What are we making u?
Square root of ln of x.
Actually, you don't necessarily have to make it the square root of ln of x. You could just make it ln of x. So it's either way. It's the reason you don't want to make it the square root of ln of x is because then you actually have that extra piece put in there. So if you just make it the ln of x, then du is just 1 over x, which I already have, and then I can just deal with the square root of u. So that's not that big of a deal. So this is going to go from 2 to infinity of the u to the negative 1/2 power du. So that's 2u to the 1/2. So I have 2 square root of ln of x. And I'm doing that from 2 to infinity. So if we look at that, I have 2 square root of ln of t as the limit as t goes to infinity, minus 2 square root of ln of 2. So if I look at that first piece there, is that t goes to infinity, what's going to happen to that first part? Square root of ln of infinity is really infinity. So this whole series goes to infinity. So therefore, it diverges, so the series diverges. Based on the integral test. Questions with that one? All right, next one up. This series. All right, so which test do we want to use for this one?
The root test?
Yes. So you might look at it and go, oh, well, it's got the -1 there, so I can do the alternating series test. The problem is being able to try to find the limit of that function there is going to be very difficult to do. So the root test really helps us out there. And also the root test takes into account the absolute value of it. So we don't have to worry about that -1 anyway. So this is the root test. And I'm actually going to. All right, so there's the root test. Work your way through the root test, and then we'll work on this problem.
That's the ratio test?
Oh, sorry, the ratio test, not the root test. Ours. Yes, you're actually doing the ratio test in this one, not the root test, because of the factorial. You can't do the root test and you have a factorial.
Okay.
All right, so we have these fractions. Now we have to break things up so I can cancel things out. So up there, I'm going to take that pi 2n times pi to the 2. And then I have the 2n factorial there.
Why are you adding 2 instead of 1?
Because it's actually 2n plus 1. Which is where the 2n plus 2 comes from. Because you're replacing the n with n plus 1. So since it's 2 times, you have to distribute the 2.
Oh, okay. Thank you.
No problem. And actually, that comes into play down the bottom here too, because I have 2n plus 2. To get down to the 2n, I have to do 2n plus 2. I also have to pull out the 2n plus 1. And then I have the 2n factorial. So my 2n's will cancel out. And then I forgot to write down here the pi to the 2n. That'll also cancel out. So I'm left with pi over 2, or pi to the second power, and then 2n plus 2 and 2n plus 1 on the bottom. So that's what I'm looking at the limit. So as n goes to infinity, this one. And as the bottom gets infinitely large, that goes to 0. The nice thing is, even if you screwed up and did the 2n plus 1, it wouldn't have changed the difference in the actual final answer in this problem. So since this one is 0, based on the ratio test, that's less than 1. So it is absolutely convergent.
I have a question about how in the denominator, how you got 2n plus 2 and the 2n plus 1. Where did the 2n plus 1 come from?
Because so remember, factorials basically keep going every term down, right?
Yes.
So that's the 2n plus 2 is that term, and then one space down from that would be 2n plus 1, not 2n.
Oh, okay.
And then the next one down would be the 2n, which or 2n plus 0 in essence, which is what I want to get rid of.
Okay.
So it's pretty much 2n minus 1 plus 2 is the second term down?
Yes,
Okay.
or 2n plus 2 minus 1. Yeah. All right, next one's up. All right, well, you work on this one. I'll be right back. One thing to keep in mind for this one is when you have two series, you can look at it. When you have the addition, you can split it up. So when you're looking at the series, look at each one individually. And as long as they both converge, then the whole series converges. So this one, you're actually going to use the P series and the geometric series. All right, so if we look at the 1 over n to the third, which one are we using for that one?
That's P series,
So that's P series,
and so it's convergent.
because 3 is greater than 1, so that's convergent. And the other one's going to be the geometric series. So this one ends up being 1/3 to the nth power. So my ratio is 1/3, which is less than 1. So therefore that is also convergent. So the whole answer is convergent. If either one of them diverged, the answer would have been divergent. Because the divergent one will always pull anything that converges basically to a divergent at the end. All right, next one. Let's do some trig functions in there. All right, what are we going to do for this one? This one you're going to look at a comparison test. However, when you look at the comparison test, you're going to start off with the absolute value. Because sign goes back and forth between positive and the negatives, so you have to look at the absolute value version of it. So what am I going to compare this one to? Hold on one second. Sorry, I have somebody fixing my dishwasher and I had to shut off power to it. Okay, so this one we're going to compare. So the first thing I want to do is I'm going to take that sign 2 over 1 and change it to 1. Because I know that it's always going to be less than or equal to 1. And then I can say, well, that is always going to be less than 1 over 2 to the nth power. Does that part make sense? Can we hear me or no?
Yeah, I
Okay.
kind of makes sense.
All right. So the goal when we're trying to compare things, we're trying to find something that is either always less than or always greater than. If it's always greater than and that diverges, we're good. If it's always less than and that converges, we're good. So since I know the sign 2n is always going to be less than 1 or equal to 1, I can say I know this function here is always going to be less than or equal to that function there. I'm not saying it's equal to it. I'm just saying I know it's going to be less than or equal to that. So I can use that as a comparison. And then as this is getting bigger and bigger, so if I'm adding 1 here, this right here is always going to be less than this, or the 2 to the n, because it's 1 less than I have. So I know this one's always going to be less than it. The reason I want to get down to this part is because this right here, that's a geometric series. So that one, I now have 1 over 2 to the n. So r is 1/2, which is less than 1. So that part converges. And now based on the comparison rule, as long as that series converges and it's all in the series, the original series is always less than that series. So we're using this one right there. That means that series right here has to converge.
All right, that
You
makes sense.
You can use anything you want to compare as long as you can always show that the series that you have is always going to be greater than what you started with. So you just want to try to get something that's easily workable, and that's where the geometric series and the P series comes into play quite often. All right, next one up. What do you think we're going to try here? So if we go back and look at our things, this isn't a p-series, it isn't a geometric. We really can't do a quick test for divergence with this one. Because finding limits probably going to be a little complicated with just this piece here. It isn't alternating. So not really a candidate for the root or ratio tests.
So we have
It's
to.
got the addition. So you could do the integral. We have one other limit. We have one other comparison test that we also can try too. That's that limit comparison test. So the limit comparison test, remember, we're looking at if we can compare it to something that might be easier to deal with. Because I actually think trying to find the integral of this would be very messy. Because it's not like we could just do a quick U substitution or anything else in there. So let's see if we can compare it to something. Remember, when we're looking to compare this, now when we're doing the limit comparison test, it doesn't actually have to be greater than or less than. We just need something similar to compare it to. So in this case, I'm just going to use 1 over n. And there's no real rhyme or reason to use it. If this works, great. If not, we can try 1 over n squared. Because this one I know diverges. And it's got some ends in there. We might be able to cancel some stuff out and come up with a limit that might actually work out kind of nice. This is just one of those things that we have to test.
So you just pick the B of n. It doesn't. There's no like real.
Nope. There's no real like rule. You have to do it this way. Like in the last one, when we looked at the comparison, I said, okay, we got to make the S of n because we were trying to compare it to something that was greater than or less than that piece. In the limit comparison test, I technically can use any one I want. It's just a matter of trying to find one that's going to help me simplify down the problem. Because remember, in the limit, I'm dividing it. So when I'm looking at this problem here, I'm taking my original function. So I have my limit as n goes to infinity of the square root of n to the 4th plus 1 over n to the 3rd plus 3 n. And I'm dividing that whole thing by 1 over n. So I got to pick something that's going to help me like simplify this down. And the nice thing about this one is what it does. What's up? Give me 1 minute. I'm sorry. I'm running up and downstairs. All right, so now let's finish this one. So we have square root of n to the 4th plus 1. I can factor out an n on the bottom here. That's why you can use, if you use 1 over n, it works out really nice. Because now those two n's cancel each other out. And I have n to the 4th plus 1 over n squared plus 1. So now I can divide everything by a single amount. And the bottom is not going to cancel. It will not totally cancel out. Because now if I divide everything by n squared, I get 1 plus 1 over n to the 4th over 1 plus 1 over n squared. And that limit goes to 1. Now the rule for this one says, as long as the limit is a finite number greater than 0, which this is, both series converge or diverge. I know this one diverges because that's a harmonic series. So my original function has to diverge. Does that make sense? All right. All right. Next one. All right. Which test should we use for this one?
Alternating series.
Yep. We're going to use the alternating series test again for this one. So there's just a reminder what the alternating series test is. All right. So which one of the two criteria do you want to try first? Do we want to look for the limit or do we want to look for decreasing?
Decreasing.
All right, so to do decreasing for this one, because it's not obvious, because we have the ln on top and the square root on the bottom, we have to do the derivative for it. So we have to find f prime of x. So we do f prime of x, we get 2 minus the ln of x over 2x to the 3/2. Because you're doing the quotient rule. So now on this one, we want to look at when this one is less than 0. The bottom can never be negative. So we're literally just looking at the top. So I have 2 minus ln of x has to be less than 0. So ln of x has to be greater than 2. So that means x has to be greater than e to the second power, which is fine. So I know this is going to be decreasing when n is e to the second power or higher. So it does decrease given time. Now we have to look. So we've met the first criteria. Now we have to look at the limit. So I'm looking for the limit as n goes to infinity of ln of n over the square root of n. Now on this one, the only way for us to determine the limit is to actually do L'Hopital's rule on it. So we're going to do the derivative of the top and the derivative of the bottom, and then we look at the limit as that one. So I have the top is going to be 1 over n, and the bottom will be 1 over 2 square root of n. So simplifying this down, I have 2 square root of n over n, which ends up being 2 over the square root of n. So that limit is going to go to 0. So it meets the second criteria, and therefore it is convergent based on the alternating series test.
What was the name of that rule again?
L'Hopital's. You'll see it in the books a lot of times. It'll have the equal sign under it, and it'll put a little bit like an H over it. That's the symbol for it when you see it in the books. The rule basically states as long as if you take the derivative of the function that you have and do the limit of that one, it comes out. It'll still give you the same rule, the same information as if you did the limit of the original series or the original function. It's in, I think it's in section 3 or chapter 3.2 or 3.3, where they actually talk about it. All right, next one's up, 32. All right, so which test should we do for this one?
Ratio.
The ratio test? Yes. No, not the ratio test. This one we're actually going to do the root test because they're both raised to the nth power.
Okay, but what about the factorial?
We're going to be left with the factorial after we do the root test because we're going to get rid of that nth power and then we can work with it.
Okay.
Because the top and the bottom both are raised to the nth power, we're going to eliminate that basically with the ratio test. All right, work on this one. I'll be right back. Okay. Last time. The guy's leaving now. So we're doing the root test for this one. The first thing we want to do is change this to this. And then when I do the nth root, it's going to get rid of that. So my limit as n goes to infinity, it's n factorial over n to the fourth power. Now, if we look at that, the n factorial on top is going to get larger a heck of a lot faster than just n to the fourth down the bottom. So this function, it goes to, the limit goes to infinity because the top's going to get higher than the bottom. So since it goes to infinity, it's divergent. Any questions with that one?
So is it okay to assume that if the factorial is in the numerator, we can do the root test, and if it's in the denominator, the ratio test?
No. So the only reason we could do the root test on this one is because there was an nth root actually in the problem that I could cancel out using the root test.
Okay.
So in the last one we did, when I said we couldn't do the root test, we had to do the ratio test. That was this one. Notice how the top had the nth power in it,
But
but the bottom did not.
Okay.
So I couldn't get rid of the nth root doing it that way. That's why we had to do the ratio test for that one.
Okay.
But this one's got it on the top and the bottom, so we were able to do it. All right, one more. Last one. All right, so what do we want to try for this one?
Could we just use the divergence test?
So if you did the limit of this one, what are you going to get? As n goes to infinity, the bottom's going to go to what?
0.
Right. So I guess you could. Because the bottom's going to go to infinity. So the bottom's going to go to infinity. Well, no, actually, that won't work. That's why. So the bottom's going to go to infinity. So the fraction's going to go to 0. The divergence test says it can't go to 0. It's when the limit doesn't equal 0. This limit does equal 0. So if you did the limit as n goes to infinity of this, that would go to 1 over infinity, which is 0. And the test for divergence says it can't equal 0.
So wouldn't that just make it convergent? Is that
No, the test for divergence doesn't ever tell you convergence.
Okay.
It just tells you it divergence. So if it fails the test for divergence, we know nothing. That would make our lives really easy if we just had to basically test the limit, and if it went to 0, we knew it converged. But remember, 1 over n would go to 0, and it diverges, and 1 over n squared doesn't. That one converges and goes to 0. So that's why that test doesn't really help us.
Okay.
So this one, we're actually going to do a comparison test for it. So if I look at the bottom here, so we got 1 over n plus n cosine squared n. So I know, because cosine squared and any of the cosines, it's going to go between 1 and -1. I know it's going to bounce back and forth between those two things. So 0, I know this is going to be, and since it's cosine squared, it's never going to be negative. I know that's between that and that. I know it's going to be bigger than 0, and I know it's going to be less than or equal to n for that. So I can say that this function right here is going to be always bigger than 1 over n plus n. Since it's on the bottom, this function down here is always going to be bigger than that's going to be. And that's the same thing as saying 1 over 2n. So and now the 1 over 2n, does that converge or diverge? That's the question. So if I looked at the limit n equals 1 to infinity, or sum of 1 over 2n, that's actually the same thing as saying 1/2 of the harmonic series. So this diverges. And since this diverges, and this is always bigger than it, this diverges. So. All right. Any questions on that one? Okay. So let me end this.